we wanted to do it last week, but somehow we had to postpone it today. And then
correct. Okay. Anyway, this is okay for me.
thank you so much.
Yes.
হ্যালো রামদা,
হ্যাঁ বলো।
বলছি কি মানে কি প্রবলেম কি?
প্রবলেম হচ্ছে আমি একটু অপেক্ষা করি, অ্যাটেন্ডেন্স জাস্ট আসছে।
ও আচ্ছা আচ্ছা, হ্যাঁ, একটু আচ্ছা
এক এক করে বাড়ছে আর কি। তো আমরা শুরু করবো, তো ভাবলাম যদি একটুখানি রেসপেক্টেবল ফিগারটা আসে তাহলে আমরা শুরু করবো আর কি।
ওয়েল নো প্রবলেম নো প্রবলেম।
না 5 মিনিট হয়ে গেছে অলরেডি, আমরা আর অপেক্ষা করবো না। অলরেডি উই আর 21 people on the webinar. চঞ্চল,
Yes.
হ্যাঁ তো শুরু করবো?
Yes. We start.
Okay then, because already
I think the people
Uh,
will be started joining.
yeah, people will be joining, I think.
Yeah.
Anil Kumar Pandit has given micro inputs for nanotechnology. Okay, that's fine. Sudeep, are you ready? Good afternoon, dear participants and our experts and our chairman with Bengal State Center IEI and Deputy Director Technical Sudeep Chakraborty, our moderator for this afternoon, my dear brother Chanchal Chakraborty. We are starting our webinar on nanotechnology. We have experts as our Professor Manidipan Shahu from IIT Dhanbad and co-speaker Madam Monika Kumari. She is also from IIT Dhanbad. I will now request our chairman, Dr. Nirmal Das, with Bengal State Center IEI, to give his welcome address. Over to Dr. Nirmal Das. Chairman, sir.
I think he got dropped.
Oh.
He's not there.
Okay, he was
He
there.
got dropped. Just 1 minute. Just a minute. I think now he has joined.
I think.
Yeah. Ramda.
Mr. Chairman, sir, please give your welcome address.
Well, it's a very good evening. On behalf of West Bengal State Center, the
Chairman, sir, audio ta thik nahi.
Institution of Engineers India, I would like to welcome you all the participants, all the. Hello. Am I audible correctly?
Yeah, we can hear you, please.
So I'd like to welcome you all, particularly today's guest speaker, Professor Manidipan Shahu from IIT Dhanbad, Madam Miss Monika Kumari from IIT Dhanbad, and they'll be talking about nanotechnology, the most emerging field of the day, and the session will be moderated by Mr. Chanchal Chakraborty, convener of Electronics and Telecommunication Division. I would like to welcome our Ramchandra Chakraborty, his joint honorary secretary, our honorary secretary Dr. Raju Boshak, who will be giving vote of thanks in due course. All other participants, ladies and gentlemen. Today's topic is nanotechnology. As you know, nanotechnology, often shortened as nanotech, is the use of matter of atomic, molecular, and supramolecular scales of industrial purpose. Nanotechnology is the control of matter at the nanoscale at dimension between approximately 1 to 100 nanometers, where unique phenomena enable novel applications. Matter can exhibit unusual physical, chemical, and biological properties at the nanoscale, differing in important ways from the properties of bulk materials, single atoms, and molecules. Some nanostructured materials are stronger to have different magnetic properties compared to other forms or sizes of the same material. Others are better at conducting heat or electricity. They may become more chemically reactive, diffract better, or change color as their size of structure is altered. All new natural materials have been used for centuries. Gold and silver nanoparticles created colors in the stained glass windows of medieval churches hundreds of years ago. Nanotechnology encompasses nanoscale science, engineering, and technology in the fields such as chemistry, biology, physics, material science, and engineering. Nanotechnology research and development involve imaging, measuring, modeling, and manipulating matter between approximately 1 to 100 nanometers. The potential impact of nanotechnology processes, machines, and products is expected to be far-reaching, affecting nearly conceivable information technology, energy source, agricultural product, medical device, pharmaceutical properties based on nanostructured materials offer the possibilities of confirming, steering, and separating light by wavelength on unprecedented lasers that require very low currents to initiate lasting, called near threshold lasers. These structures have been extensively investigated as the tools for nanostructuring materials. Interested in the informational control is not as stringent as the shorter visible wavelengths, and where optical communications and chemical sensing provide motivation for potential new applications. Today, the two eminent speakers who will be presenting, they are the very good renowned person in this field, and I hope all the participants will enjoy today's lecture, and let's see what advancements will be discussed today. And I welcome all you once again and wish you the grand success of this webinar. Thank you very much.
Should I start?
Ramda.
I have been muted. Okay. Thank you, Mr. Chairman, for your welcome address. And as Mr. Chairman has elaborated on the theme, I will not repeat that. I will directly go to introduce our esteemed speaker this afternoon. We have panelist Dr. Monideepan Sahu. He is assistant professor in the Department of Electronics Engineering, Indian Institute of Technology, Dhanbad. Popularly was known as ISM Dhanbad. Dr. Monideepan Sahu received MTech in Instrumentation Technology from IISc Bangalore in 2006. He received his PhD degree from IISc Shibpur, India in 2016. His PhD thesis was on modeling and analysis of carbon nanotube and graphene and nanoribbon based interconnect. He is currently serving as an assistant professor in the Department of Electronics Engineering, Indian Institute of Technology, formerly Indian School of Mines, Dhanbad. His research interest includes modeling and simulation of nano interconnects and nano devices, biosensors, Internet of Things. He has published more than 50 articles in archival journal and referred conference proceedings. He has also published, sorry, I have skipped one line. His research interests include modeling and simulation of nano interconnects and nano devices, biosensors, Internet of Things. He has published more than 50 articles in archival journals and refereed conference proceedings. He has also published a book entitled Modeling and Simulation of CNT and JNR Interconnects with Lambert Academic Publishers in 2019. He published a book chapter entitled Modeling Interconnects for Future VLSI Circuit Applications with IET Publishers in 2019. He is also associated as a senior member of IEEE, fellow of IET, member of IEI, and life member of Instrument Society of India. We are proud to have such a learned member of IEI. We have the second panelist at Madam Monika Kumari. She is research scholar in the Department of Electronics Engineering, IIT Dhanbad. She received MTech degree in Electronics and Communication Engineering from IIT Dhanbad in 2018. She is currently pursuing a PhD degree in the Department of Electronics Engineering at the same institute under the supervision of Professor Monideepan Sahu. Her current research interests include nano devices and biosensors. Now, I introduce our moderator this evening, Mr. Chanchal Chakraborty. Of course, he needs no introduction because he has been moderating n number of sessions. He is BE MBA, having more than 35 years of professional experience in telecom and IT. He worked with flagship companies like CSC, NTPC, Department of Telecom, BSNL, and worked as Chief Technology Officer and Vice President in Aircel, Uninor, and Reliance Jio. Wide experience in planning, design, procurement, installation, and maintenance in all fields of telecom. Currently is working as Executive Director and Chief Executive Officer of ATM Towers India Private Limited, a subsidiary of ATM Denmark. He participated in several national and international seminars, including GSM Congress at Cannes, France, and Berg for international roaming. He has received different accolades, including the Vishish Sanchar Seva Award from the Ministry of Communication, professionally associated with IEI India as a fellow member, and he is also Secretary ISA Kolkata section, a team player and loves to serve society to the best of his ability. Now over to Chanchal. Please take charge for the session.
Thanks, Ramda. So now we'll directly invite Dr. Manodeepan Sahu to present his session and followed by his co-speaker. So over to you, Dr. Sahu, and the platform is yours. Thanks.
Thank you. Good evening, all the attendees, and I'd like to thank Dr. Nirmal, Dr. Ram, and Dr. Chanchal for inviting me for this talk. And so we'll start with the session now. So as the attendees have already got a brief overview of what we are going to address today, which is the topic on nanotechnology. And as you understand, this is emerging also, you can say, and also relevant in today's world, looking at the prospects of so many different type of applications. Those are possible through nanotechnology. Okay, so the slide transition not happening.
I think you have to start again.
And then you have to start. Yes.
Sometimes you switch it off and then
start again. Yes. Okay. Is it visible, this current slide?
Yeah, absolutely.
Okay. So now we'll move into the brief background of this area, huge area on nanotechnology. So people have been using the nanomaterials for more than 4,000 years. In fact, the term was not coined, nanotechnology term was not coined, but before that people used to basically having different applications of nanotechnology, okay, like different kind of nanoparticles, their emission, and based on that different colors that we see in different natural objects. Those are nothing but nanotechnology only. 1959, formerly renowned physicist Richard Feynman first coined the term And in fact, he laid the foundations for the nanomaterial revolution. And then the nanotechnology as a term was, taken and was coined by Nario Taniguchi in 1974. Okay, and then the nano term basically means that it is dwarf. It is coming from the Greek word dwarf. That means the reduced dimension, in different dimensions when we reduce it. So then it is called nano size. Now what is nano? We'll come into the next slide. In 1981, Drexler described a new bottom-up approach instead of conventional top-down approach for synthesizing nanomaterials. We'll come, consequently, we'll come to bottom-up approach and top-down approach in the later in some slide. So first we'll discuss about the different breakthroughs, scientific breakthroughs that has happened in the in the years. So in 1996, first of all, the Nobel Prize in Chemistry was given for the discovery of fullerene. So this was the first, you can say, the discovery of one nano form particle, that is the fullerene, which is a zero-dimensional form of carbon. And then in 2010, Nobel Prize in Physics was given for the studies in graphene. And after 2010, there was numerous number of papers that were published in graphene. In 2016, the Nobel Prize in Chemistry was given for molecular machines. Now, molecular machines have become, excellent revolution in the field of machines. So it is basically the, you can say, the miniaturization of the machines and how you are going to use those for different applications. So that is really, exciting. And apart from this, there have been numerous scientific breakthroughs resulting in countless scientific papers being published. Many products have been manufactured and so on. So we'll see different applications of this. So what is nanomaterial? So we'll discuss about the nanomaterial, its physics, and then we'll move to the different applications of nanomaterials. So nanomaterial is a material which have at least one of its dimension in nanometric scale of the order of 100 nanometer or less. Okay. So if you compare the size of a nanomaterial with human hair, you can see that almost 3 orders of magnitude difference you have with human hair. So that is the level that we are talking about in terms of technology, and that is the reason it is also called nanotechnology. So nanomaterials possess a significantly higher surface area compared to their volume. This is the reason being that the dimension is reduced in different directions, and that's why the volume that it contains will be reduced. However, the effective surface area will increase, and this enhances the chemical reactions, adsorption properties, and interactions with other substances. At nanoscale, also the quantum effects become more pronounced, which can influence the optical, electronic, and magnetic properties. The reason behind that we'll discuss when we discuss about the physics of different nanomaterials. Certain nanomaterials such as graphene and carbon nanotubes exhibit exceptional strength, stiffness, and resilience, and that's why graphene finds its use in different mechanical application wherever you need a very strong material for the stability of those materials. And then we come to the physics of nanomaterials. Here we will discuss different topics on quantum confinement effect, then the density of states, then the Brillouin zone, and then we'll discuss about the transport properties and their measurements, the magnetic properties, and the optical properties. First, we'll discuss about the quantum confinement effect. So quantum confinement effect is well known to most of you. I know the attendees all have actually gone through this kind of physics in their class 2 level or in the graduate level. The quantum confinement basically leads to the fact that there are the particles or the electrons, you can say, in this case in the atomic scale, those are confined in their movement. Okay. So quantum confinement means the confinement or the restriction of the movement in different dimensions. So here we talk about 0D, 1D, 2D, and 3D. So 0-dimensional and 1-dimensional, 2-dimensional, 3-dimensional quantum confinement, and what it leads to in terms of the properties. So the implication of quantum confinement is in its properties. We will see that how it is related. So in the bulk materials such as a macroscopic piece of a semiconductor, the energy levels available to electrons are continuous and form energy bands. However, in nanoscale materials, the size confinement restricts the motion of electrons in certain directions, and this leads to the discretization of the energy levels. Okay, so if you have the constrained movement of electrons, let's say in the case of zero dimension, the movement of the electron is constant in all directions, then the energy levels are discretized. Okay, in fact, that is also true for one dimension, two dimension. In three dimension, it is not constrained; it is free to move. The electrons or the charged particles, they can move freely in all the dimensions. So this basically leads to quantized energy states, and by precisely controlling the size and shape of nanoparticles, researchers can tailor their optical and electronic properties. Why it is so? Also we'll discuss in the subsequent slides. So this allows for the development of novel materials with improved performance and in a wide range of applications. Now you see some of the examples that are given. Zero dimension, we have the application as fullerene. Fullerene is a zero dimensional form of carbon, as I said earlier, quantum dots and gold nanoparticles, which are examples of zero dimensional materials. One dimensional material examples are nanotubes, carbon nanotubes, metal nanorods, nanowires. There are n number of applications that you can find for 1D form of nanomaterial. Then we come to the two-dimensional form. Examples are graphene, layered materials, layered nanomaterials like MOS2, that is molybdenum sulfide layered material, and as well as other 2D nanomaterials, the carbon coated nanoplates, etc. The three-dimensional, we have the polycrystalline form of material, dendrimers, liposomes, all are three-dimensional form of nanomaterial. Now we move to interesting aspect of this in the physics point of view, that is the density of states. Now, as we constrain the movement of carriers, mostly the electrons, in different dimensions, the density of states also varies. Now, what do we mean by density of states? It means that the number of energy states available per unit volume per unit energy. Okay, and that we can understand because there is a discretization of the energy states. So naturally, the density of states will also vary with the confinement of the dimensions. Okay, so the density of states is given by Ge equal to 1 by V multiplied by dN dE. Now dN by dE, that is a derivative of the number of electrons for energy. So per unit energy, how many energy states are available, and then the number of electrons at a given energy. So this is the number of energy states available for occupying. So those number of electrons will be occupying, and then divided by the volume. So that will give you the density of states. Now Ge here represents the density of states at a given energy E, and the rest of the parameters I have already discussed. Now the implication of this density of state in terms of the dimensional confinement is depicted here in this diagram. So first we consider a bulk material, which is a three-dimensional form of material where the density of states is parabolically related to the energy. That means with higher energy, the energy density of states will increase. However, it will saturate at a certain point. It will not indefinitely increase with energy. However, that is a continuous variation of density of states with respect to energy. In the case of quantum well, which is a two-dimensional form of material, here we can see that if we say this is as x direction, so this x direction is confined, however y and z direction is not confined. Okay, and that relates to the density of states. The impact of that on the density of states we can easily observe here, that there is a step increase in the the energy level. And as I said earlier, quantum confinement leads to discretization of the energy states. So here we have the energy states E1 that is occupied here, and then there is a sharp change in the density of states at E1, and then it remains constant over energy difference of E1 to E2, and then again at energy level E2, the density of states, there is a sharp variation, sharp increase in the density of states. So this way the density of states varies for a quantum well structures, and it is well known for quantum well structures. Now for quantum where even there is further variation in the density of states, again different discrete energy levels, there is a sharp variation, and then not only that variation is there, but the density of state doesn't remain constant in between the energy levels. Okay, what happens in between the energy levels? The density of state doesn't remain constant, it also decreases. Okay, again when it reaches the subsequent energy level, again it sharply increases and then it drops again. So this is the nature that we observe for quantum wave. It is vastly different from what we have seen for quantum wave structure and for the bulk. Next, the quantum dot, we can see even the discretization phenomena that we can perfectly observe for quantum dot structure. What you see here is that only at the discrete energy levels you can see a appreciable density of states. The rest, apart from that, all the other energies, the density of states is zero. Okay, so only the electrons will be occupied those particular energy levels. That is the significance. And now the question comes that what is the significance of this? Significance of this comes to that the properties that we see for this material. So the same material in the bulk form will show some property. In the quantum well, it will show a different property. Quantum where the property may significantly vary, and that is the power, you can say, the significance of why we are utilizing nanotechnology here, because nanotechnology can give you the properties that you cannot expect in the bulk form. Okay, now some of the key physical aspects that we need to learn. One we have discussed is density of states, another is the billowing zone. A billowing zone is something that is related to the crystalline nature of the material. Okay, so we consider crystalline solids mostly for fabrication or synthesis of different kind of nanomaterials. Now crystalline solids have an interesting property that the atoms are arranged in a periodic manner, in a periodic form, in a regular manner orientation. So what happens, that periodicity relates to in the reciprocal lattice. So this is the real space. In the reciprocal space, if you look at, that is the k space, where the k is basically the wave vector. So when we think of this material from its real space in the k space or the reciprocal space, we get interesting properties or interesting information that we can gather of the material. So that is depicted here. So this is the k space, this is the k space representation of the same crystalline solid, and then this is the band diagram. So this is the energy variation with respect to the k, that is the wave vector. For this material, any crystalline material, we can observe this band structure, which is formally known as band structure or energy band structure or EK diagram. Okay, so billowing zone is defined as the region in the k space that contains all possible wave vectors for electrons in the crystal. So what it determines is that what are the different movement of electrons that are possible and which direction it will move. Okay, so that basically relates to the transport properties of the material. So the transport properties of the material is inherently related to the billowing zone of the particular material, crystalline solid that we are talking about, and it plays a crucial role in determining the electronic properties, as I said. So within the billowing zone, the electronic band structure of the material is represented by energy bands, where we have the several sub bands also can be seen. Conduction band, valence band, conduction sub bands are there, valence sub bands are there, and that will basically determine whether the material is semi-conducting in nature, metallic in nature, insulating in nature, what kind of bandgap is present in those material. All this information can be gathered from this EK diagram. That's why it is so important. Now coming to the another physical aspect, that is the transport properties and their measurements. So transport properties meaning that how the carriers, that is electrons, phonons, holes and photons, so all these different type of carriers, how do they move? Okay, so inside a crystalline solid we can see the movement of electrons or holes in the case of semiconductor and phonons, okay, mostly. And how do I determine the transport? There are interesting theory behind it, that is the dimension of the material related to the mean free path of the particular material. Okay, so particular means that we are talking about that what kind of mean free path exists for the particular material. So now according to that, the transport can be segregated into three different type of transport. One is called the diffusive transport, quasi-ballistic transport and ballistic transport. So what is diffusive transport? In the case of diffusive transport, what we consider is that the dimension of the material is far larger than the mean free path. Now mean free path is a term that in a basic physics class I think you have got the idea that mean free path basically relates to the path that is traveled by an electron when it moves from one collision to the next collision. Okay, so that is the mean free path. It is a statistical parameter that we measure for any carrier. In the case of electron also, hole also, we can measure it. Now if the dimension is far greater than the mean free path, then it is called diffusive transport. That means there are the scattering phenomena that happens with electrons with other carriers. Okay, that is the phonons and other defects, impurities, etc. And thereby we describe the mobility of the carrier. Mobility means how the carriers move inside a material when we apply an electric field across the material. So this kind of transport where there are scattering, there is diffusion mechanism. So there is drift and diffusion mechanism, both exist, that is called a diffusive transport. In the case of quasi-ballistic transport, the dimension is equivalent to the mean free path. So in that case, the significance of scattering is not there, but there are appreciable that we need to consider the effect of scattering also in the transport. So that's why it is not a ballistic transport, it is a quasi-ballistic transport. Now you need to understand what is ballistic transport. When the dimension is less than the mean free path, then the probability of collision when the carriers move from one end to another end is far less. So in that case, the movement is almost free without any collisions, then that's why it is called ballistic collision. Okay. Now this basically governs the transport properties of the material. Now we move to the different methods that we use for measurement of electrical properties. One of the method is 4-probe method. Again, by the diagram I will explain. So this diagram shows that this is the material that we have and we apply a constant current supply across it. So what will happen is that the current will flow through the material. So the current source is connected and then current will move through this material, and thereby the resistivity of this material will determine that what kind of voltage drop that we can expect. So if we connect a high impedance voltmeter, another 2 probes are connected to high impedance voltmeter, so then that will measure the voltage drop across the 2 probes. The reason behind this measurement called 4-probe method is that there are 4 probes used. 2 probes are called current probes and 2 probes are called voltage probes, and through the current probes we excite it by a current source and then we measure the voltage. So this voltage measured will determine the resistivity or the resistance of the material. Okay, and that resistance of the material gives you idea about the electrical property of the material. Now we move to another property, that is the Hall, using the Hall method that we determine, that is the magnetic property. Okay, so any material, all of you are aware of Hall technique. So in the Hall method what we do, it refers to a technique used to measure the Hall coefficient and determine the carrier concentration and mobility of charge carriers in a material. And it involves applying a current to a sample and measuring the voltage developed across the sample. However, it is different from photo method. The reason behind that is it is placed inside a magnetic field. So, in the transverse direction perpendicular to both the current and the magnetic field, the voltage will be developed. So, this material has to be placed inside a perpendicular magnetic field, which is orthogonal to these two directions where we apply the current and where we measure the voltage. So, the Hall voltage is proportional to the product of the magnetic field, current and the Hall coefficient. So, by measuring the Hall voltage for different magnetic fields and currents, it is possible to determine the Hall coefficient, which is related to the carrier concentration and the mobility of charge carriers in the material. And this is an interesting method, and this Hall effect gives rise to measurement of carrier concentration and the type of carrier or the doping of a semiconductor can be determined using the Hall method. Now coming to the magnetic properties, nanomaterials exhibit interesting magnetic properties too due to their small size and unique structural characteristics. So nano-sized magnetic particles or clusters often exhibit super paramagnetic behavior, and super paramagnetism occurs when the thermal energy is sufficient to overcome the magnetic anisotropy energy barrier. As a result, the magnetic moments of the particles randomly fluctuate between aligned and unaligned states, causing a net magnetization of zero in the absence of external magnetic field. And magnetic properties of nanomaterials can vary depending on their size. As the size decreases, number of atoms or ions at the surface related to the bulk increases, leading to enhanced surface effects, and these surface effects can influence the magnetic behavior. So nanomaterials can exhibit different types of magnetic anisotropy, which determines the preferred orientation of magnetic moments within the material, and shape anisotropy arises from the shape of the nanostructures, where elongated or non-spherical shapes lead to different magnetic behaviors along different directions. One of the example and application of that is giant magnetoresistance, and this is one of the application can find for nanomaterial as giant magnetoresistance effect and tunnel magnetoresistance effect that we can see. Now coming to interesting property, that is the optical property that we observe, and that happens because the light source interacts with the matter, and the matter, if it is a nanomaterial based matter, then light interacts in a different manner than it interacts if it is a bulk one. Okay, so it intriguing optical properties due to their unique size, shape and composition that we observe. Here are some key optical properties observed in nanomaterials. First one is the plasmon resonance. Plasmon resonance, it is a collective oscillation of electrons in a metal nanoparticle in response to incident light, and then there is a plasmon that is formed, or plasmon resonance gives rise to the enhanced electromagnetic fields in the vicinity of nanoparticles. This is an interesting property that we can only observe in the case of nanoparticles, okay, having that property, making them useful for applications like sensing, surface enhanced Raman scattering and localized heating. Now another interesting property, the optical property here, that is the photoluminescence. Now photoluminescence lead to the fact that when nanomaterials, first of all they are excited by photons, and then what happens, there are transition, electrons transit from lower energy state to higher energy state, and then after excited by photons, those electrons again lose the energy and move to different intermediate energy states, and that particular phenomena is called photoluminescence, where there is a luminescence that arises from the nanomaterial because of the transition from higher energy state to lower energy state, and it loses energy in the form of photon. And other luminescent nanostructures also exhibit size dependent emission properties due to quantum confinement effects. So by controlling the size and composition of nanomaterials, the emission wavelength and intensity can be precisely tuned, and this is an interesting property that people make use of in displays. Okay, different kind of displays are coming now, quantum dot LED and other displays are coming. So the concept is photoluminescence that they use, and optoelectronics imaging different bioimaging and other imaging applications, photoluminescence. Optical absorption and scattering is another application. Here, the nanomaterial, when the incident light, is exciting the particular material. So the exposed material, when it is exposed to the incident light, it basically absorbs the energy from the light, and then it emits or scatters or transmits that particular energy in different form. Okay, and then the transmission happens at a different wavelength. Okay, so different type of, so the wavelength that it absorbs and wavelength that it emits are different, and that leads to different kind of applications of this. So the high surface to volume ratio in nanostructure increases the interaction between light and the material, leading to enhanced absorption and scattering of photons, and this property is also utilized in different applications like solar cell, photodetector, and coatings, optical coatings. Now we move to the second part of this lecture, that is I think I am late little bit, so I will move little faster. So fabrication techniques, which is also equally important. So how do you synthesize different type of nanomaterials? Okay, so for this there are two principal approaches. One is the top down approach, another is bottom up approach. And top down approach, what you do, you take a bulk material, larger structure, and then gradually you move to the nanoscale by breaking it down. Okay. So there are methods like etching, milling, grinding, different mechanical methods are there, lithography method are there to move from bulk form to the nanoscale. The bottom up approach is the opposite, that is you move from the chemicals or the atomic or molecular form and then you grow to the nanomaterial form. So that is the bottom up approach, and it is based on the self assembly of the different molecules that they come in close proximity, they assemble together and then they synthesize a particular type of nanomaterial. Okay, the technique used are mostly the chemical methods like chemical synthesis, self assembly, sol gel processes, and the vapor deposition processes. It is depicted here. So this is the top down approach, where from the bulk form to the nanoscale we can move, we can fabricate, and the bottom up from the molecule atom form to the clusters, then the nanoscale. So the different fabrication methods. First one is a sol gel method. Now with the help of diagram you can explain it easily. So you have a solution form, okay, so colloidal structure in a solution form, and then you have the nanoparticles that is already immersed in the solution, and then you do the condensation. So the solution containing the precursor and the solvent. Precursor means that the material that you want to deposit or you want to synthesize, and the solvent that will hold this precursor. Okay, so that will make a solution called sol, and then what happens, you condense this solution, that is sol, to gel form. So what happens after condensation, the relative distance between the molecules or atoms will decrease, and then it will form a gel kind of structure. And then after supercritical drying, thermal drying, and freeze drying, so there are different drying techniques, you form different type of gels. So aerogel, xerogel, and cryogel. So these are different kinds of gel formation from the sol. So that's why this is called a sol gel method. Here we are forming a nanomaterial in the gel form. Okay. Now electrochemical deposition, this is a well-known technique. People have already come across this technique earlier, that we use two different electrodes, and then the material that we want to deposit will be in the solution. Electrochemical solution will be consisting of the ions, metal ions that we want to deposit, and then there are anode and cathode. So where we will deposit, so metal ions will be positive, so it will be deposited on the cathode. So cathode will be having this electrode, and the anode will be having the metal electrode will be the anode electrode, and from the anode all the metal ions will come in the solution, and then by applying suitable potential, that is the electrochemical potential, those ions from the solution will get deposited on the cathode. So this way the electrochemical method works. Then we move to the vapor deposition technique. There are two principal vapor deposition techniques. One is the chemical vapor deposition, another is physical vapor deposition. In the case of chemical vapor deposition, what happens? You deposit a thin film by chemical reaction occurring in a gaseous environment. So you have a substrate, and you have a gaseous, so evacuated chamber only having the gases that you want to, the gaseous environment that you want to have for deposition of the particular electron. And those gases will react and deposit a solid material onto the substrate surface. So in the case of chemical vapor deposition, the substrate will be there. So I think we have a picture for better depiction of the phenomena. So we have this chamber. So the substrate is placed here, the bottom, and then this chamber is exposed to different inlet gases and outlet gases, and this chamber contains all the kinds of reactions that happen. Okay, and the gases will react, and after reaction, the end product will be deposited on the substrate. And this may require external energy in the form of heat. Okay, so that energy will be given externally, and thereby it may lead to the required deposition we can achieve. Now we have the physical vapor deposition. In the case of physical vapor deposition, there is no chemical reaction happening inside the chamber. Instead, you apply an electric field or a potential across the substrate and the target. Now the substrate is placed in the bottom, connected to ground. There is a sputtering gas that will be placed, that will be inlet into the chamber. Now what will happen, that the sputtering target, that means this material will be deposited on the substrate, so the target has to be placed here. So now if you apply a high potential across this target and the substrate, what happens, the atoms will be getting dislodged from the target material, and then they will be transported by the vapor or gas that is present here. It will transport it down to the substrate, and with time this substrate will get a deposition of a thin film of the target material. That may be a metal, that may be an insulating material, anything that you want to achieve. Apart from that, you need to maintain an inert atmosphere because we don't require any chemical reaction here. So argon atmosphere is kept inside the chamber. So this is a physical vapor deposition technique. Now this particular technique is also called a sputtering technique. Now this sputtering technique can be further divided into multiple techniques. That is called DC sputtering technique, RF sputtering technique, magnetron sputtering technique, and then we have the reactive sputtering technique. In the case of DC sputtering technique, we apply a DC potential across this. Okay, so in this case only we can achieve metal deposition on the substrate. In the case of insulating material deposition, you require a very high electric field. Then DC sputtering is not at all applicable. We need to apply a very high potential. So instead of applying a very high potential, we apply an RF field across it, which can break down the the target, and then gives rise to the bombardment. Can be even eased by plasma formation. RF, so this RF power will generate the plasma, and that will ease the or facilitate the bombarding of the target. Rather, the sputtering phenomena will be facilitated, and there will be deposition of the material on the substrate. Then further, the sputtering efficiency can be improved by placing the sputtering chamber inside a magnetic field. Then it is called a magnetron sputtering, by directing the charged particles or charged atoms in a particular, or ions in a particular direction by magnetic field. So that is called the magnetron sputtering. Through magnetron sputtering, you can achieve higher deposition rate, better uniformity, and better sputter efficiency with a wider range of materials than both DC and RF sputtering technique. Now reactive sputtering technique is another interesting one, and nowadays people are using this instead of chemical vapor deposition. This is also another reactive kind of sputtering technique, where you need to ensure that there is some reaction happening inside the chamber, and that reaction will give rise to the particular material, nanomaterial deposited, and nitrides and oxides can be deposited using reactive sputtering technique. It has wide application in semiconductor manufacturing, because in semiconductor manufacturing you need to deposit different kind of coatings, okay, optical devices, optoelectronic devices. magnetic storage media and decorative coatings, we need reactive sparkling technique. This is the chamber that we are having. Then the pulse laser deposition method, this is the same as earlier, that this is a deposition, physical deposition method. However, here the laser beam is used to bombard the target. So the target is placed here, it is continuously rotated. The laser beam targets different portion of the material of the rotating target, and after the bombardment there is a laser plume formation, and that these particles will be forming a plasma here, and from there it will get deposited onto the substrate. And again, the chamber has to be vacuum. It should not contain any other particle except the target particle that you want to deposit for the purity of the film or the nanomaterial that you want to deposit. Now the spin coating technique. This is a chemical technique where you have a liquid solution or dispersion, and you place that onto the spinning substrate. So the substrate is placed and that will rotate or spin, and onto that you place a liquid solution. Now what will happen with the movement, with the rotation of the substrate, the liquid solution will also get spread out, and it will form a uniform and thin uniform coating because of the centrifugal force. And this is depicted here. So you have the spindle plate of the spin coater, it is rotating, and this substrate is there. You have the coating solution. So what happens with the speed, the rotational speed, what will happen? This will spread out, and finally when the solvent gets evaporated, you will get a thick solution that is deposited in the form of a thick material, nanomaterial on the substrate, which is what we expected. Now another interesting technique is a mechanical technique, is a ball milling technique, where we grind the materials into fine powders, and those powders can be further used for different application like zinc oxides, titanium oxides, semiconductor materials, which can be ground, and then the ground powder, the powder form, can be used for different applications like nanowares of various materials, including metals, semiconductor and oxides. Now coming to the self assembly, it is a bottom up approach. Contrary to the other approaches, those are top down approaches. This is the bottom up approach. In the bottom up approach, what happens? The molecules come closer because of the electrostatic forces, van der Waals forces, and the bonding, chemical bonding forces, hydrogen bonding, etc. So they assemble together and then they form a nanomaterial. So this is explained here. So you have the molecules here, which are the building blocks, and after the molecular self assembly, they assemble form a module. Then we have the geometrically they come in close proximity with each other. Now this happens because there is attraction, molecular attraction, different attractive forces are present, that leads to the modular assembly, which is called the mesoscale assembly, and this is of the order of 100 nanometer or even higher. Okay, this kind of method is used in assembly, self assembly technique. Now we come to the lithography technique. Now lithography technique play a crucial role in nanomaterial fabrication, especially the semiconductor fabrication. Okay, so different type of lithography is used, that is optical lithography, electron beam lithography, nano imprint lithography, and so on. What is optical lithography? In the optical lithography, you pattern nanoscale features using optical method, that is light. Okay, so you have a you have the substrate, and on the substrate you want to create a pattern. So how do you create a pattern? So for that, first of all, a photoresist. Photoresist means it is a photosensitive material that is deposited first on the substrate, and after the deposition of the photoresist, you expose that photoresist and deposited on the substrate, that particular object or material, to the light, UV light, and then UV light will basically based on the pattern. So you have a mask, you need to place mask in between the UV light and the photoresist deposited on the substrate. So what happens, the mask will allow the UV light to pass through in certain portions and will not allow in certain portions. So the portions that will allow will lead to either hardening or softening of the photoresist. So thereby you create pattern. So there are two kind of pattern that can be formed. One is called the positive, because of the positive photoresist, this pattern can be formed, and because of the negative photoresist, this pattern can be formed. Now these positive photoresist and negative photoresist, these are different chemical materials. Basically these are having different chemical properties, which leads to either hardening or softening of the photoresist. So what we have done, because of this, there is a pattern that is formed on the substrate, you can clearly observe. Now the same thing we can do using a electron beam. Now why we are moving to electron beam instead of UV light? The reason behind that, features, the nanoscale dimension features cannot be formed by photolithography. So we take the help of electron beam, and then electron beam exposure to the material. Again the same method, you have the positive electron beam resist or negative electron beam resist deposited on the substrate, and the pattern is formed by suitably masking this exposure to the substrate. Then the nano imprint lithography. In the case of nano imprint lithography, what happens? You have the silicon or silicon oxide mold, you have a thermoplastic polymer film, and that is directly in contact with the substrate. Now if you heat it, because this is a polymer kind of substrate that we use nano imprint lithography, if you heat it, what happens? Because of heating and the high pressure, the certain portions of the substrate will get melt, and after it get melted, what happens? That portion will create a pattern here. Okay, and when it cools down, that will remain, this pattern will remain. So this is only applicable for substrates which is having thermoplastic polymer or polymer substrates or thermoplastic polymer kind of thing. And the same can be also possible for transparent quartz mold, as explained here. Now we come to the characterization techniques. Okay, so different characterization techniques. So why characterization techniques are required? So characterization techniques are required to determine whether we are getting or we are able to achieve the desired property out of the shaped nanomaterials. So nanomaterials are shaped by our different techniques. We need to characterize those. Okay, so for that different techniques are used. First one is the scanning electron microscope. To the scanning electron microscope, the electron gun emits electrons, and then it is directed by a magnetic lens in a particular direction, and then the specimen containing the stage is exposed to the directed electron beam, and after that the backscattered, so electrons get scattered, and then we detect and measure the backscattered electrons by a backscatter electron detector, and thereby we can measure the features, the morphology of the particular or topography of the specimen, and also measure the energy dispersive X-ray spectroscopy of this particular specimen. Through SEM, we can determine the features, morphology, composition also. This is a standard scanning electron microscopy image of a molybdenum sulfide powder. And then the transmission electron microscopy, this is also another microscopy technique. However, this provides even valuable insights and finer insights into the structure, composition and properties of material, enabling researchers to study the characteristics of nanomaterials, investigating the defects in crystalline materials, etc. This is for the nanomaterials of nanometric dimension, we prefer TEM more than SEM to understand the finer features, and you can clearly observe that the features are even finer in the case of TEM image, tunneling electron microscopy image. Now atomic force microscopy, this is another microscopy technique where the cantilever is used, having an AFM tip, that is the atomic force microscopy tip, and then we have the laser. So this laser is directed to the tip and it is reflected and it is getting detected. If the features are uniform, what will happen? The photo detector will detect a constant light in a particular direction. However, if the features are non-uniform and there are certain dip and the variation in the depth of the material or the surface, then what happens? The photo detector will determine or detect the light from different directions, and it will measure the surface or the topography in a finer scale, that is the nanometer scale. We can determine the surface morphology, and we can clearly observe that 10 nanometer. So of the order of nanometer, we can measure the features, the dimension, that is both in the width direction or the height, that we can easily measure using atomic force microscope. Then coming to another very important characterization technique, that is called the X-ray diffraction. In the case of X-ray diffraction, is used to determine the crystallinity or crystal nature of a material, and then from there the composition of a material can also be determined using X-ray diffraction. What is the concept? Concept is that if the material is having crystalline nature or non-crystalline nature, so what will happen is that the X-ray source will get diffracted from the different crystallographic surfaces, and when it gets diffracted, the diffracted beam is measured or rather gathered, and then that diffracted beam is basically an indication of the different atomic spacing of the crystalline material. Now that atomic spacing information gives you whether it is a crystalline nature or not, and if it is crystalline, then what are the different crystalline planes are present, and which is an indication of materials. Okay. Now this is a XRD pattern that is shown here. We can see the intensity of the measurement, that is the X-ray beam that we measure, the intensity of that at different diffraction angles. This is 2 theta because we are measuring the back diffracted light. Okay, so it is the incident light at an angle theta, diffracted light another angle theta, so there is 2 theta angles. So we measure, and that is called the Bragg angle also. So different XRD peaks are measured, which is an indication of crystallographic planes of the particular material. Now Raman spectroscopy is another very important and sophisticated spectroscopy technique to understand the finer aspect of a material. Those are related to the vibrational modes, okay, of a nanomaterial. Vibrational modes means when a material is excited by photons or excited by a laser beam, then that happens that there is transition of electron from one state to another state, and those states are called vibrational states. Okay, and those give you indication of atomic transitions, or rather you can say the variation or the property varies, electronic property variation can be understood, and that is measured by passing a laser beam onto the sample, and then a monochromatic laser is used with visible or near infrared wavelength, and then the laser interacts with the sample, and a small fraction of the scattered light undergoes a change in energy due to interactions with the sample's molecular vibrations or rotations, and this energy change leads to a shift, which is popularly known as Raman shift in the wavelength of the scattered light, resulting in the Raman scattering. So the output of a Raman spectroscopy experiment is called a Raman spectrum. This is a typical Raman spectrum that you observe after the measurement. So this is the Raman scattering intensity, this is the Raman shift. Now the Raman shift, the unit of that is 1 by lambda. That means it is the measurement of, you can say, the frequency shift or the energy shift that you can measure, which basically these peaks are called Raman peaks, and this shift basically relates to the different vibrational energy change or shift inside the material. This is extremely important for the chemical analysis, understanding the molecular bond formation. Okay, so for understanding the electronic level or molecular level bonding formation and all, we can detect using Raman spectroscopy. Next is the UV visible spectroscopy, where again a monochromator is used to direct from a single polychromatic light to a single wavelength or monochromatic light, and then it is passed to the sample, and the sample, when it is exposed to a narrow band wavelength light, then it basically emits different photons. Okay, so the photons, the light that is coming out of it, the scattered light from the sample. Okay, that is measured and that gives rise to the UV visible spectroscopy. This is called UV visible spectroscopy because we use an UV range or visible range of wavelength to analyze the optical property of materials such as semiconductor, nanoparticles and dyes for application in electronics, photonic and material science. This is a typical UV visible spectroscopy, the plot that we get with respect to the wavelength. Now, types of nanomaterials. So first we will discuss about the carbon based nanomaterials, and carbon based nanomaterials are segregated into mainly the 4 forms. One is called the diamond, that is a 3-dimensional form of carbon. Then the graphite, which is a 2-dimensional layered form of carbon. Then fullerene, which is 0-dimensional form of carbon, and nanotube, which is 1-dimensional form of carbon. All of these forms of carbon are extremely useful in different day-to-day applications. Okay, diamond people know. Graphite is used for conducting applications because it is having very high conductivity, and then nanotubes are also used for different sensing, field effect transistor and sensing applications, and fullerenes are also used for different quantum dot applications. Okay. Now, metal based nanomaterials are also in use in ages. So we are using different metal oxides for decades. Okay, like zinc oxide, titanium oxide and tin oxide, all those are used for different displays, different coating, okay, transparent coating, etc., conducting films, and then flexible electronic, touch screen, solar cell, all find use. And also the silver nanoparticles exhibit unique optical, electrical and antimicrobial properties, whereas gold nanoparticles possess the exceptional optical properties such as surface plasmon resonance. Iron oxide nanoparticles include the magnetite and magnemite properties, exhibit the magnetic properties because it is iron oxide nanoparticle. They are extensively utilized in magnetic resonance imaging, drug delivery, hyperthermia therapy and environmental remediation. Copper nanowires are elongated nanostructures with very high electrical conductivity. Now we come to the different applications of nanomaterials. So electronics and optoelectronics is the first, energy storage, biomedical applications, environmental applications. However, it is not limited to these 4. There are numerous number of applications that can arise in future. Electronics and optoelectronics applications are nanowires, nanotubes, okay, and quantum dots. Those find widespread use in electronics and optoelectronics. Nanomaterials such as graphene, carbon nanotubes have shown promise in transistor technology, as I said earlier, because they are having excellent conducting property as well as semiconducting property. So they can be used both as a conductor as well as semiconductor. That's why they find use in several electrical application, transistor applications. Quantum dots, semiconductor nanocrystals with tunable emission wavelengths have been utilized as color converters in quantum dot LEDs. And quantum dot LEDs, you know the widespread application, commercial application of quantum dot LED. Nanomaterials have facilitated advancements in the field of nanophotonics, where light is manipulated at the nanoscale. Now we come to the another use case, that is the energy storage and conversion application. In the energy storage, the application is in terms of batteries, supercapacitors, piezoelectrics and thermoelectric, and also solar cell, LEDs, etc. So nanomaterials like silicon nanowires or graphene have been explored as electrode material to achieve very high energy density. Carbon nanotubes, graphene have been used for supercapacitor applications because of their very high or fast charging and discharging rates, excellent electrical conductivity, efficient energy storage and rapid power delivery. Nanostructured electrodes such as carbon nanotube and nanostructured oxides facilitate efficient fuel and oxygen transport, enhancing the overall performance of fuel cells. Apart from that, the piezoelectric and thermoelectric applications also, interesting applications that we get out of nanomaterials. Okay, and nano lubricants, nano refrigerants, smart windows, superconductive materials, all you can achieve using nanomaterials, carbon based nanomaterials or metal based nanomaterials. Now coming to the biomedical applications. Biomedical applications like tissue engineering, drug delivery, photothermal therapy, gene delivery, etc. can be well achieved by using different forms of nanomaterials like carbon nanotube, graphene, fullerene, etc. Okay, and here the iron oxide nanoparticles find widespread use in contrast agents in MRI and CT imaging. Gold nanoparticles also can be used for different imaging applications, fluorescence imaging applications. Now we come to the environmental applications. For the environmental applications, mainly the ecosystem that we are talking about. So the graphene oxide carbon nanotube metal organic frameworks have been used for water purification purpose. Titanium dioxide nanoparticles can be used in photocatalytic coatings to break down air pollutants like nitrogen oxides and volatile organic compounds under sunlight. Nanosensors can detect and quantify pollutants, gases and toxins with high sensitivity and selectivity. Like titanium oxide, zinc oxide, tin oxide, they have been used for decades for gas sensing application, different chemical identification, odor identification, etc. They enable real-time monitoring of environmental parameters and early detection of contaminants in air, water, and soil. Nano encapsulation of agrochemicals enhances their controlled release, improves their efficacy, and minimizes leaching into the environment. So, widespread use of nanotechnology in environmental applications. However, although there are prospects, huge prospects, but there are challenges, and also we'll briefly describe the future directions. So challenges are many because the fabrication at the nanoscale itself is a challenging job. So although we are able to fabricate from top down approach and bottom up approach, but the impressive results are only possible at the lab scale. However, massive production or the commercial level production is still a challenge, and it is a hurdle also. So as with any emerging technology, the environmental and health impacts of nanomaterials and nano devices need to be thoroughly studied and understood. And there is a separate branch that has evolved recently, that is called nanotoxicology, which is the interaction of the nanomaterial with the biological species. So that leads to toxins, formation of toxins and toxicity, which has to be measured. Okay, we don't know at the nanoscale what kind of toxicity that it has when it comes in contact with the biological species. So that is something that we need to also look into, apart from its exciting prospects. And we can see that this domain is not a you can say like a branch, rather it is a unity of multiple branches. You can say interdisciplinary branch, that is the nanotechnology, which needs or requires the expertise of electronics, materials, nanobio field, metrology field, sensor technology field, etc. When people from different backgrounds will come, then only exciting applications of nanotechnology we can achieve, like quantum computing, memory, photovoltaic application, processor application, printing, automotive, aerospace application, drug delivery, tissue engineering, forensics, structure, environmental application, consumer application, security, planetary science, medical application, etc. So in conclusion, I'll conclude my talk here. In conclusion, nanotechnology has emerged as a transformative field of study and research, integrating knowledge from various disciplines such as physics, material science, fabrication techniques, and characterization methods. By manipulating matter at the nanoscale, scientists and engineers have unlocked new possibilities for designing and creating advanced devices with unique properties and functionalities. The precise control over the composition, structure, and morphology of nanomaterials has led to breakthroughs in fields such as energy storage, catalysis, sensing, and biomedical applications. Fabrication techniques have evolved significantly to meet the demands of nanotechnology, from top-down approaches like lithography to bottom-up methods such as self-assembly and molecular synthesis. Researchers have been able to fabricate nanoscale structures with remarkable precision and complexity. From electronics to optoelectronics to medicine, energy, and environmental sustainability, nanotechnology has the potential to revolutionize industries and address global challenges. Okay, so these are the references that I have used, and so we'll take up the questions after the next talk at the end of my students talk, and you can connect me to this mail ID, and this is my web page. So any information you want to have, you can always drop me a mail or connect me. Thank you. So should we move to the next talk?
Yes, please. Yes, please.
Okay, thank you. So I'll close it here. Now I request my student to start the talk on biosensors. So she is my PhD student, Miss Monica Kumari, and she will be delivering the talk on biosensors. Yes. Screen sharing now. Okay, so okay, so I'll basically open the presentation. Now can you present? इधर आ जाओ. Are the slides visible now?
Yeah, visible.
Okay, so she will present now.
Good evening to all of you. Am I audible?
Yes, ma'am. We can hear you.
Okay, thank you. I would like to thank my supervisor, Manodeepan sir, for giving me this opportunity, and I would like to thank all the panelists for giving us a platform to present our work and to share some insight about the nanomaterials and the work we are doing on nano-based materials and basically in nanotechnology. So my area is related to nanomaterial based dielectric modulated PET biosensors. I'm working on the PET bed biosensors. So I first I will give a brief overview of biosensors, then I will move forward with dielectric modulated PET based biosensors, and then we have also worked in some advancement in dielectric modulated PET based biosensors, so I will discuss about them. Then I will discuss about the TMDs, like 2D material, transition metal dichalcogenized, why we are shifting to TMDs, and the work, the architecture modification that we have done to improvise the sensitivity of a biosensor. And at last, I will discuss some of the fabrications, results, characterization, and the process we are working fabricate a biosensor, just like an application based biosensor that we are working right now. Okay, so basically what a biosensor is. In crude sense, we can say a biosensor is a device that integrates biological elements and transduction technology to detect a specific kind of analyte, to detect a concentration of that particular analyte in a particular sample. Or we can say that the fundamental purpose of a biosensor is to convert the biochemical interaction between the biological component and the target analyte into a measurable signal, so that we can get some valuable information about the presence and the concentration of the analyte. So now I will discuss about the basic components of a biosensor. Basic component of a biosensor consists of biological component. The biological element of a biosensor can vary, like just like we can say we can use enzymes, antibodies, nucleic acid like DNA, RNA, anything, and this work as a receptor. And then there is a analyte, that is a specific kind of analyte that we want to detect. The receptor work as a probe that conjugate with the analyte and then give us a measurable kind of signals, like a biochemical event occur between the analyte and the receptive layer, and the biochemical reactions result in a signal, measurable signal through a transducer that can be measured by us. So we can detect what kind of changes are occurring, what kind of biological phenomena, a biological or chemical reaction that happens between them, that can be measured through the signal processing technique via the transducer. So what happens first? First, the biological component, like the receptor, we have to find a particular receptor for a particular analyte. Not every analyte is receptive to every kind of probe molecule or a receptor. First, we have to find both the analyte and the receptor layer. We then have to understand the binding event between the receptor and the analyte. After that, we can move through the transducer. What kind of transducer we want to work with to get the biochemical signal into a measurable electrical signal. That can be electrochemical, optical, any kind of transducer we can work. And that the output signal is processed and analyzed via appropriate electronics and data processing technique for the measurement. So basically, every biosensor we work on have some kind of specific features. These features are that a biosensor should be highly specific. It means it will be able to respond to a particular analyte in a group of analyte. Second, it should be biocompatible. Biocompatible means it should prevent the adverse reaction between the sample, and moreover, it should not damage the sample that we want to work with. Third one is sensitivity. A biosensor should be highly sensitive. It means it should be able to detect even the lower to lowest concentration of the biomolecules. Fourth one is selectivity. It means it can specifically recognize and measure target analytes between the number of analytes and between the number of interference like salt or different kind of molecules present. Fifth one is linear response. So the response should be linear so that we can be able to measure that response. And the last one is fast time response. Means we want real time. If we want real time monitoring, the point of care detection, so the response should be fast enough so we can detect it. These are the various applications that a biosensors have, like food analysis, study of biomolecules and their interaction, drug development, environmental field monitoring, agriculture industry, medical diagnostics. Like in healthcare, biosensors play a crucial role in diagnosing disease, monitoring patient conditions, and detecting biomarkers such as glucose monitoring for diabetic patients or detecting pathogens are very necessary in medical. So these are the applications where you can easily found any kind of biosensors. So since we are working on a fat-based biosensor, so these are the some specific qualities of a fat-based biosensor that should be looked for. First one, it should be in small size and weight. should have level 3 detection. Level 3 detection means the biomolecules that we aim to detect should be level 2. Like we should not have labeled it like using a forensic dye or a radioactive active isotope, because it makes the fabrication and the detection process very complex. So it should be a level 3 detection. It should be compatible with CMOS fabrication technology. This is very necessary in today's area, because it should be able to fabricate with the circuitry, rest of the circuitry we are working on. It should be ultra sensitive, as I said. It should be able to detect the lowest amount of concentration. And that biosensor, the special quality is that it is very low cost. It is able to fabricate in product. It is able to produce in mass. So since biosensors are being investigated from the very long time, the dielectric modulated phase-based biosensor was first fabricated by the group that belonged to Y.K. Choi in 2007. What happens in a dielectric modulated phase-split biosensor? This is basically a this is basically a MOSFET, as all of you can understand. So what is done? A sacrificial rail, just like chromium, is deposited between the oxide and gate, and this layer works as a sacrificial layer. By using wet etching or rising, this layer is etched, and then a vertical nano gap is carved, and in this gap the biomolecules are being functionalized. There are various kind of functionalization techniques that need to be studied before the functionalization is being done. After the functionalization of the biomolecules, the capacitance of the gate below basically the gate capacitance get modulated. And since the gate capacitance get modulated, the surface potential will change, the current will change, and we will be able to measure the changes before and after the functionalization of a biomolecule. So this is the basic principle of a dielectric modulated phase-split biosensor. It works on the modulation of dielectric. So as time is going and there are continuous scaling in the CMOS industry, so there are limitations of dielectric modulated phase-based biosensor that we have studied, which are due to continuous scaling, short channel effects has become a constraint for biosensors. Second one is the ultra sensitive biosensors are the need of power to detect even a lower concentration of biomolecules. And third one is as the device dimension decreases to nanoscale, abrupt doping profile between source and channel, just like the doping is changed between the source and channel, has given rise to challenges in fabrication of short channel MOSFET. These are the limitations that is we have studied in DM phase-based biosensor. To resolve these issues, we have suggested a dual material double gate stack engineered junctionless MOSFET based biosensor. So this is the architecture that we have designed to mitigate the problem of the conventional dielectric modulated phase-split biosensor. In this, we have used a junctionless MOSFET, like source, channel, and drain all have same kind of doping. Junctionless devices have uniform doping, as all of you know, between source to channel to drain, and it can be in the form of PP type or NN type. So it can make the fabrication really easy, and it is also being able to mitigate the short channel effects and also improve the ion-off ratio. Apart from this, we have also used dual metal gate. Dual metal gate, like two metal in the gate. Like gate is consist of metal 1 having a different kind of work function and metal 2 having the different kind of work function. So we have used dual metal gate to avoid the screening of drain potential, to avoid the issues of Tibble. Then we have used high K, low K dielectric to enhance the sensitivity of our architecture. So principal contribution of this architecture is through the modeling of this particular DMDG junctionless MOSFET based biosensor. So we have developed a 2D analytical model for this, incorporating several design parameters like high K gate oxide, in the gate oxide stack, cavity length, charge of biomolecules, impact of gate oxide stack with different high K dielectric materials on the electric characteristics of the biosensor has also been studied. Sensitivity metrics of a biosensor, that are change in threshold voltage, change in drain current, ion-off ratio, are also studied. And after this, we have validated our model with the well-known simulated PCAT simulator. So this is the analytical modeling approach. This is a well-known analytical modeling approach. So in this approach, 2D analytical modeling is most preferred to obtain the surface potential. By solving the 2D Poisson equation, we will be able to find the surface potential profile in every region. Just like we go to the architecture, we have divided the region in 3 different regions like L1, L2, L3. L1 and L3 are the region carved from the dielectric to form a nano gap where the biomolecules are being functionalized, and L2 are the normal oxide gate based architecture. So there are 3 regions we have created, and in every region we have to solve the Poisson equation to find the surface potential. So to find the potential distribution of each region, the Poisson equation is being solved separately, and then the well-known parabolic approximation for the potential distribution in each region is defined. Here A0i, A1i, A2i the coefficient of this expression. To find the values of this coefficient, we have to apply the boundary condition at the SiO2 interface. So after applying the boundary conditions, I think the boundary conditions are the well-known boundary condition that satisfy the continuity of electric displacement at the interface of oxide and the channel. So after applying the boundary conditions, and doing some mathematical calculation, the surface potential for each region can be obtained. So this is the potentials like phi 1, phi 2, phi 3 and phi 4 are for all the regions. So after that we will do a linear approximation and we add all the potentials together to find a complete surface potential profile of the channel. So after this, how to find the drain current of that particular biosensor? First of all, we have used a sub-threshold region. We all know that in sub-threshold region, the biosensor gives us the highest sensitivity. So the drain current in sub-threshold region is obtained by the equation that I have mentioned. It is a well-known equation in the MOSFET, totally in MOSFET industrial MOSFET environment. I have used this sub-threshold equation in ID sub, and then for the linear profile in the linear region, I have used the ID linear current that is easily being used by everyone. So these are the linear current profile in every region, like ID linear 1, ID linear 2, ID linear 3. And by doing some mathematical organization and doing some MATLAB code, we will be able to conjugate the ID sub and ID linear together to get a complete current profile of that biosensor. So these are the results that we have found out after the modeling and the simulation process. This is the surface potential profile that we have got for different kind of high K dielectric. The low K dielectric is SiO2, which is constant, and we are changing the high K dielectric like titanium oxide, hafnium oxide, aluminum dioxide, and SiO2. So what we have seen, as the high K dielectric, as the dielectric constant of the dielectric increases, which result in decrease in central channel potential. This depicts that the requirement of higher gate voltage to deplete the channel will increase, which cause an increase the VTH. As you can see, with the higher dielectric, there is a decrease in central channel potential, which leads to an increase in the higher demand of threshold voltage. This is the sensitivity profile of the biosensor. For any biosensor, sensitivity calculation is of utmost importance. So how to know how much the biosensor is sensitive, how much the amount or how much is the value, we will be able to differentiate between before and after the conjugation of biomolecules. The sensitivity parameter is able to give us. So the sensitivity parameter is defined by the threshold voltage having a dielectric constant of a biomolecule greater than 1. So the biomolecules that we are conjugated here, we have taken its dielectric constant as its characteristic or its property. Like K equal to 5 is a dielectric constant of protein. K equal to 3 is a dielectric constant of biotin. So we have extracted different values of dielectric constant of different biomolecules, and we have applied different values of dielectric constant and calculated the sensitivity. So the formula that we have used here for sensitivity is the value of threshold voltage when K is greater than 1 minus VTS at K equal to 1. K equal to means when there is no biomolecules, like only air is confined in the cavity. So you can see with the titanium dioxide and SiO2 combination, the sensitivity is high. And in this figure, we have plotted the sensitivity with respect to the variation in the cavity length. We have optimized the cavity length and see that between 25 to 35 nanometer, the sensitivity remains same. Like when we are increasing it from 50 to 20 to 21, the sensitivity will be increasing. But after the it remains saturated. So we have found out that the 35 nanometer of cavity length is the optimized value of the cavity that we can go for. This is the Ionoff ratio. The Ionoff ratio, it is also a sensitivity parameter that we use to calculate the sensitivity of PET-based biosensor. So for the dielectric constant K equal to 10, the Ionoff ratio we are getting is around 10 to the power 13, which is a very good Ionoff ratio. At last, this is the threshold voltage and sensitivity calculation for the charged biomolecules. Like every biomolecule has a dielectric constant, it also contains some charge. Like DNA, positively charged DNAs are there, negatively charged DNAs are there. So we have taken the different value of charge of biomolecules, and then we have calculated the threshold voltage and sensitivity particular kind of charged biomolecules. For negative charged biomolecules, since when we are integrating the negatively charged biomolecules, the fragment voltage will increase, which leads to increase in threshold voltage. So the threshold voltage here is increasing. And for the positively charged biomolecule, we have found that the changes are there, but changes are not very prominent. But for negative charged biomolecules, the changes are very good and these are the sensitivity. For charged biomolecules, the formula that is used for calculate the sensitivity is the threshold voltage for neutral biomolecules minus the threshold voltage for charged biomolecules. These are the benchmarking of our work with different contemporary literatures available. So as you can see that the sensitivity that we have got is better then the contemporary architecture, like when there is split gate, there is junction link, gate surrounding, gate underlap, a single metal double gate. So this is basically a silicon-based electric modulated FET-bit biosensor that we have improvised, and we have tried to mitigate the problem that the conventional DFT biosensor were facing. After this, we have switched to 2D material. As such, as sir has already mentioned, that this is the most intriguing semiconductor for the next generation. So we have also studied TMD material for our biosensing purpose. So why are we shifting to TMDs? There are some of the most specific qualities of TMDs that making it uh, making it to lead against the silicon-based biosensors. Just like it is a planar structure, it has high surface to volume ratio. Because it has a planar structure, the surface to volume ratio it has is more as compared to silicon. It doesn't have any dangling bond, so scattering is very less, leakage current is very less. It has tunable band gap. It means by increasing or decreasing the layers, bilayer, monolayer, trilayer, we can tune the band gap. It has vulnerable forces, weak vulnerable forces between the layers, so it can easily exfoliate it into different number of layers. And not to mention, it has high carrier mobility, and obviously it is compatible with the modern fabrication technology. So basically, this is a basic structure of a MOS2. This is a unit cell that I have mentioned, and when I want to make a device, I want to repeat that unit cell. So this is the side view and this is the top view of that unit cell. So MOS2 has a crystallographic form of 2H, which is semiconductor, and it has hexagonal structure. So MOS2 in TMDs, apart from MOS2, there are WSE2, MOSE2, WTE2 that we are also looking for our biosensing purpose. So we have also worked on the 2D material TMD FET-based biosensor for label-free biosensing, and we have developed a analytical model for that biosensing, and we have also published a very good working scientific report. So this is the two structure that we have focused on. First one is without the gate over the cavity, and the second one is gate over the cavity. Since there is no gate over the cavity, so the fringing field will dominate, and as in the second structure there is no gate, there is gate over the cavity, so the fringing field will be very less and the gate control will be good. So we have studied both the architectures and we have developed a model for that, and this is a brief introduction of the modeling part that we have covered. Since the equations are very clumsy and very large, so we are not able to include all the equations. These are the final equations that we have included. This is the surface potential distribution. Since the channel is very thin, so we can create a infinity small in this channel we can create a infinitesimally small area, and we can find the Gaussian profile of that area. We can find the charge enclosed and electric field that is going out through the Gaussian profile, and we will come to this particular equation number A, which will give us the surface potential distribution in the channel. Since there is cavity, so the channel region can be divided into three parts, like the channel region under the cavity, the channel region where there is no cavity, and the channel region again there is cavity. So it is three regions. So we have to find the surface potential profile in all the three regions. So we have used this particular equation, and the closed form solution of this differential equation is also mentioned in equation B. So this is the two basic equation that we have used. Again, thus modeling of surface potential in the overlap regions. Overlap region that we have mentioned here is region 2 and region 3. So the surface potential distribution is pi 2. here x minus L1. X minus L1 is the x is the total length direction and L1 is that cavity part that we have subtracted. The second one is the modeling of surface potential in the nanocavity region. The nanocavity regions are L1 and L3 as I have mentioned. In both the structure, the flatband voltage. Then how to define the flatband voltage in that particular nanocavities? Since the nanocavity contains biomolecule, so it will have some specific charge. So we have denoted the charge using NF and C effective. C effective means the effective capacitance of that cavity. So the flatband voltage of the cavity part would become equal to the flatband voltage of the overlap region where there is no cavity minus the charge and the effective dielectric constant of that cavity. So modeling of the surface potential for the device structure 1, as you can see there is no gate over the structure, so the fringing fields are dominant. So we have to include the fringing capacitance in the effective capacitance. So to include the effective capacitance, we have used Cox with fringing, but Cox1 plus C fringing. To calculate the fringing capacitance, there are some mathematical calculation that we have done, and after this we have come to this particular equations. For reason 1, for device structure 1, the closed form of expression I have mentioned is like phi1 is equal to C3 e to power x, C4 e to power x plus A1 by P1. And in reason 3, the closed form of surface potential is also H1. Now we go to the device structure 2 for the modeling of surface potential in nanocavity region. For device structure 2, since there is gate over the cavity, so the fringing fields are less dominant. So in calculating the effective capacitance, we are not taking the effect of fringing capacitance. We are taking the effect of the oxide and the capacitance of when the biomolecule are conjugated or not. We are taking the effective capacitance of that. After that, we are doing the drain current modeling. To model the drain current in subthreshold region is calculated by utilizing expression of surface potential that we have obtained in the previous section, and we are putting the surface potential expression in the ID sub. And for linear regime, we are applying the 3 transistor modeling approach that already been modeled in the papers that I have mentioned, and we have used drift diffusion phenomena to calculate the linear current. Now by integrating the linear current in the particular region, like from 0 to L1, like L1 to L2 and L2 to L3, taking the linear current profiles. And by adding the ID sub and ID linear, we will get the whole current profile of our channel. This is the surface potential profile of the TMD based biosensor. As you can see, due to the fringing effect, the gate control is less. So the threshold voltage, so the surface potential is going down when we compare to the device structure 2. The surface potential, the barrier is more in structure 1. So the electrons will require more voltage to pass the barrier through the source and channel as compared to structure 2. And then when we are increasing the dielectric constant of biomolecules in the cavity, the surface potential volume will go down in both the structure, but it will remain less in structure 2, as you can see from the profiles. Now we are moving forward to the threshold voltage and sensitivity calculations. Figure 14 depicts the threshold voltage variations. As you can see, the threshold voltage variation is less with the increase in dielectric constant. From the surface potential profile, it is already mentioned that the barrier is going down, so obviously the threshold voltage requirement will be less and the dielectric constant of the biomolecule will get increased. And the red one is the sensitivity that we have plotted. The sensitivity for the higher K value we are getting is more when we compare it with air, like K equal to 1 means air. And figure 15 is for sensitivity profile. The sensitivity, we are using the formula like threshold voltage when there was air and threshold voltage when the biomolecule are being conjugated. Both the plots are for when dielectric constant is being measured and when charge of the biomolecule is being measured for both the structures. We have also added the effect of partially filled cavities. Since in practical scenario we have studied and we have seen that uniform filling is not possible in the cavities, because when the biomolecule are being conjugated or hybridized, they already take the place and they hinder the conjugation of the new biomolecules they want to get conjugated. So the filling is not uniform. In theoretical calculation for our in theoretical calculation we take uniform phenomena to avoid complex calculation, but to add practical scenarios or the fabrication process scenario, we have to take the uh, impact of partially filled cavity. So here we have also added the impact of partially filled cavity in the process. So first one is completely filled cavity. Second one is cavity when the cavity is 66% filled. Third one is when the cavity is 50% filled, and last one is 33% filled. We have taken for this, we have varied the thickness of gate. In the modeling part, we have varied the thickness, like for uniform filling, we have taken the thickness around 10 nanometer. For 66%, we have thickness taken around 7 nanometer. Likewise, we have decreased the thickness and measured the sensitivity. As you can see, the sensitivity is more for the 60% field structure, because there will be more number of there will be large number of concentration of biomolecule. There will be automatically the sensitivity will be more, since the concentration is more, the electric constant will be more, and the response that we get will be fast and more. This one we have taken other different type of partially filled cavities, like when the cavities are filling in decreasing way, increasing way, or convex or concave. So we have also taken these 4 type of partially filled cavities in our modeling papers. Here you can see that for decreasing part, the sensitivity is more, because in the decreasing profile, the steps, the biomolecule steps are more at the source to channel junction, at the junction at the interface path, which leads to the rapid tunneling of electrons. So the sensitivity will be more, since the tunneling is since the tunneling in decreasing profile is more. So the electron will need less amount of energy, less amount of threshold voltage to cross the area, and the sensitivity of the device will be more. And what we have observed during this modeling is that for the conventional doping, it includes high manufacturing cost, complex fabrication, and the fabrication of thin channel 2D semiconductor based biosensor is not being done with the conventional fabrication process that we do with the silicon based biosensor like ion implantation. So researchers have also focused on electrostatic doping for the 2D material based device, but this method is not very energy efficient, because it requires several supply from for the drain, for the source. So it can be a cumbersome technique. So after the research, we have come to the effectiveness. We have studied the effectiveness of charged plasma TMD based biosensors. Charged plasma based biosensors, TMD, charged plasma TMD heterojunction based biosensor has not been studied till now. So we have studied that charged plasma TFET can be easily fabricated, but there is no need of various drain and source, the various supply in the drain and source region. There is no need for doping like electrostatic doping. So we have applied the charged plasma technique with the TMD and the heterojunction TFET. We have combined the charged plasma TMD with heterojunction TFET, and we have studied this in our biosensing purpose. So this is the structure of our dielectric modulated charged plasma based monolayer TMD heterojunction TFET biosensor for the enhancement in sensitivity. Here you can see we have used 2 TMD materials, WTE2 and MOS2. MOS2 is in the source region, the MOS2 is in the channel region and in the drain region, and the WTET is in the source region. So at the interface, when WTE2 and the MOS2 are being bonded, since the lattice constant of both WTE2 and MOS2 are different. Like for lattice constant of MOS2 is 3.19 and lattice constant of WTE 3.35 angstrom. So both are different. So how to match them? So we have also studied the strain impact on both the material WTE2 and MOS2, and we have applied tensile strain and compressive strain on WTE2 and MOS2 to match the lattice constant at the interface. So after doing the strain calculation, the strain parameter, after applying the strain parameter, we have come to this heterostructure at the source to channel junction. And to apply the charge plasma technique, we have a metal electrode at the source side and a metal electrode at the drain side. At the drain side, for N plus doping in the drain, the work function of drain metal electrode must be smaller than the work function of drain metal. And for P plus doping at the source side, the work function of source metal electrode must be greater than the work function of the source metal. So here we have used platinum P2 in source and hafnium in the drain, which satisfy the process of developing a charge plasma based electrode or charge plasma based device. So we have done this simulation in our simulator, TCAT simulator. In TCAT simulator for 2D, we have used the parameters like various material parameters like affinity, band gap, effective mass, mobility of both the materials, and we have fed it to Silvaco simulator and we have done our calculation. We have also validated our work with the experimental data that is not in this work. This is the drain current sensitivity that is being used. As you can see, for k equal to 9, we are achieving a subthreshold swing, the low subthreshold swing of 39 millivolt per decade for this architecture. This is far less than the silicon MOSFET based biosensor. That is the subthreshold slope of silicon MOSFET based biosensor. This is here also we have taken care of the partially filled profile, and as I have mentioned earlier, for the decreasing profile, the sensitivity, the drain current sensitivity we are getting is very high, like around 10 to the power minus 9, and these are the various profiles. These are the various partially filled profiles that we have used in our work. This is the benchmarking. We have benchmarked our work with the recent literature that have been published within 3 to 4 years, and we have benchmarked it at different values. We have also changed the VDS and VGS, but the dielectric values, we have also changed the dielectric constant, and we have measured our sensitivity from the device from different type of literatures, and we have seen that this charge plasma TFET based architecture is giving us a very good sensitivity when it is compared with these devices. Next, we are looking forward for the fabrication of our theoretical. Since we have done the theoretical part of TMD based biosensor, we are looking for the fabrication of the biosensor, TMD based biosensor. Since MOS2 is very easy, since MOS2 are being synthesized nowadays in many research groups, it is easy to synthesize, so we are focusing on the fabrication of MOS2 nanosheet based biosensor. And we are looking for the detection of glucose, since glucose monitoring is very crucial for early detection of various kind of kidney disease, heart disease, for diabetes patients. So we are focusing on glucose monitoring. Or what we have doing here, since we are using MOS2, we are trying to study, we have tried to exfoliate the MOS2, bulk MOS2 in a nanosheet. For exfoliating the bulk MOS2 in a nanosheet, we have used a hydrothermal process. Hydrothermal process, what we have done, we have synthesized the bulk MOS2 with EDA. EDA is a solvent that we have mixed with the bulk MOS2, and we have used liquid phase exfoliation, in which we have used centrifugal technique, ultrasonication for the exfoliation of the MOS2 nanosheet. You can see the MOS2 exfoliated MOS2 nanosheet we have got is slightly greenish. The greenish form showing that the MOS2 is exfoliated into sheets. Here we have done the SEM and TEM. SEM is which give us a 3D image or the morphology of any kind of thin films. So the morphology here is showing that the sheet has already been formed in SEM technique. The sheet we are showing is in the 100 nanometer profile, and the second and third one is the TEM image. In TEM image, we are able to go to the Armstrong range. We are able to see the lattice fringes of a thin film. So here you can see the fringes of the MOS2 sheet that has been formed, and this is the MOS2 sheet of TEM image in 100 nanometer, where there is a layered with a stack of sheets which is easily visible. After exfoliation and characterization, we have moved forward with the deposition of the MOS2 nanosheet over Si silicon wafer. So we have used a cheap and cost-effective technique like drop casting and spin coating to deposit the MOS2 nanosheet over silicon wafer. We have done both the drop casting and spin coating, and right now we are moving forward for the contact deposition using E-beam, and then the functionalization of the sheet with the glucose molecule, and the results are yet to come. So in conclusion, we can say that the MOS2 or TMD based biosensor are far way more sensitive than silicon based biosensor, but the fabrication, the commercialization is still on the lab. It's still limited to the research facilities or lab experimental, lab fabrication based devices. So it will take more time, I think, really much more time to be commercialized these biosensors in for the various purpose. Thank you. So any questions? We are open to questions.
Monica, can you please mute your microphone? Yeah, we will take up the questions just after 2-3 minutes. Before that, what we'll do is we will do the summary of the session today, whatever we have done so far. So I have been given the most difficult work of giving as a convener, as a summary of this report. First of all, I extend my sincere thanks to both the speakers of today's evening session. And we have seen that the nanomaterial is a material which have at least one of its dimension is in the nanometer scale, and it is typically ranges between 1 nanometer to 100 nanometer. And we have seen that the nanomaterials possess a significantly higher surface area compared to their volumes. And this enhances the chemical reactions, adsorptions, and interactions with other substances. We have seen the physics of the nanomaterials in terms of quantum confinement effect, the density of states, the Brillouin zone, the transparent properties of their measurements, magnetic properties, and optical properties like plasmon, resonance, and photoluminescence, then optical absorption and scattering. And we have seen the two methods for fabrication of the nanomaterials, like top-down approach and the bottom-up approach, which has been narrated very well. And we have seen the different methods of fabrications, including sol gel method, electrochemical depositions, and like that. And there are the two types of nanomaterials, that is the carbon-based nanomaterials and metal-based nanomaterials. And we have seen the applications in the different disciplines like electronics and optoelectronics, nanomaterials, nanostructured materials. Say, in terms of what I'm trying to tell, that there are the different materials applications, like in the quantum dots today you are getting utilized, and then the nanomaterials have the facilitated advancement in the field of nanophotonics, and then the nanomaterials like silicon nanowires or graphene are being explored. Nanostructured materials like carbon nanotubes, graphene, and metal oxides are being utilized for the supercapacitor applications. And like that, they're having very good applications in the biomedical applications, environment applications. And like that, for every technology, there will be a challenge, different challenges. And I am sure that our researchers across the globe will be able to overcome the different kind of challenges for the actual use cases for the human need. And now we have also seen a very good lecture on the biosensors, nanotechnology based biosensors we have seen. And we have seen that the biosensor is basically an analytical device containing an immobilized biological material, which can be specifically interact with an analyte like glucose, urea, drug. This is very important, and produce measurable chemical or electrical signals. And we have seen that there are the different features of biosensors, like it should be highly specific, should be tiny and biocompatible, sensitivity, selectivity, linear response, and fast time response. So they are the different, though the features are there, but it's very difficult to implement those in practice. And we have seen the different applications of the biosensors in food analysis, study of biomolecules and their interactions, drug development, environmental field monitoring, agricultural industry, and medical diagnosis. And we have seen that the different kind of technologies which have been developed, used for the, say, for example, dielectric modulated FET technology as a biosensors, it has been utilized. And we have studied its analytical portions as well as is the response on the experiments. And after that, we have seen that we can utilize the TMD materials, that is the 2D semiconductors, for the next generation biosensing. And we have also analyzed its studies in the lab, and we have developed this response, and the response curve summaries have been beautifully developed and have been depicted over here. And after that, we have seen the dielectrically modulated charged plasma-based monolayer TMD heterojunction TFET biosensors for enhanced sensitivity. And the response and the studies have been done. And it is really beautiful the way, because the fabrication portion of the MOS2 nanosheet-based biosensors have also been discussed, along with is synthesis of MOS2's nanosheet. And with these things, I'm sure that they will be coming with the technology which will be able to do as per in the Make in India drive. With these things, we again sincerely extend our sincere thanks from Institute of Engineers to both the speakers today. And now I will invite for the forum for give a quick few questions we can take. Our eminent speakers are there today, and you can put your questions over here, and our speakers are here to give you responses. Thank you very much.
Thank you, sir.
Any questions? You can open your microphone and to ask questions, or you can give them in the chat box.
Chanchal, under Q&A, there are 4 comments. You can have a look at that.
Yeah. The questions, whatever, actually they have just given.
No, those are not questions.
Those are not there.
Comments.
Actually, one gentleman, Anil Kumar Pandit, has told that the many thanks for the detailed exposure of the nanotechnology and what it is and why needed, how to make it in multiple mode, how to use it, and along with the pros and cons. I think the entire thing has been very well explained during the session. If you are having any specific questions, you can ask.
I think they can connect me over my mail ID and also the web page I've given.
Yeah.
It will be nice if the organizers can share it over this chat box.
Yeah.
So that in future, if they want to contact, maybe this time they are not able to ask questions, or it is not possible
Absolutely.
also to justify all the questions
Absolutely.
answering. So that's
Absolutely.
why it is nice if you can put it in the chat box so that they can
Yeah,
connect
yeah.
to me.
Yes, 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 yes. We can do that. We can do that. I'm putting your mail ID in the chat box.
Both mail ID and the web page.
And the web page. Okay.
Copy the web page also. They can get all the information.
Okay. I'm putting the same.
Okay.
Chanchal, if
Yes.
there is a question, may I ask Professor Raju to propose vote of
Yes,
thanks?
yes. You can do.
Yeah. Raju, kindly propose vote of thanks.
Yes, thank you very much. Is it audible?
Yes,
it is
you can hear it.
Thank you very much for giving me the opportunity to propose the vote of thanks. It is my proud privilege to extend my sincere thanks and gratitude to all the distinguished participants in this technical webinar on the theme nanotechnology, organized by the Electronics and Telecommunication Engineering Division, West Bengal State Center, IEI, through this online platform, Zoom. At the outset, I convey my sincere thanks to the panelists, Dr. Monodipan Shaw, Assistant Professor in the Department of Electronics and Electronics Engineering, Indian Institute of Technology, Dhanbad, India. Ms. Monica Kumari, Research Scholar in the Department of Electronics Engineering, Indian Institute of Technology, Dhanbad, India. My sincere thanks also goes to Dr. Nirmal Das, Chairman, West Bengal State Center, IEI, Professor Dr. Girish Srikishan Munda Dada, Chairman, Electronics and Telecommunication Engineering Division Board, IEI. Engineer Ramchandra Chakraborty, Joint Honorary Secretary, West Bengal State Center, IEI. Engineer Chanchal Chakraborty, Convener, ET Engineering Division, West Bengal State Center, IEI, and also the moderator of this program. The same feelings is also being showered to all members of the council, division board members of ETDB, and all members of the committee of West Bengal State Center, IEI, and all members of ET Engineering Divisional Subcommittee, Director Technical, IEI, and his team for their wholehearted support to make the program a success. Last but not the least, my sincere thanks also goes to all who are behind the screen, giving their silent support to make the program a success. Thank you very much. With this, we are concluding our session here. Thank you very much.
Thank you.
Thank you, sir. With the permission of chair, may I end the webinar?
Yeah.
Oyun,
So
thank you all. Thank you all.
Webinar from your end.
Yes.
So thanks everyone for the very good lecture today and on the most, the discussed the technology today. And this is the technology which is going to change the course of the entire humanity. So I think the very well it is explained, and thanks everyone, and wish everyone happy weekend. Thank you very much. I think we can close down the session.
Thank you.
Oyun, you may end the webinar from your end because you're the host now.